Did you know your OS is juggling hundreds of processes right now as you watch this video? Today, we'll dive into process management and uncover what's really happening behind the scenes. If we look at the conceptual architecture of a computer, at the core, we have a hardware which contains the CPU, memory, and I/O devices. On top of that sits the operating system, and finally, we have applications and programs. The operating system's job is to manage resources like CPU time, memory, files, and devices, so that multiple users and applications can run efficiently and without interfering with one another. And one of the most important parts of this management is process management, or simply task management. At the core of process management is the CPU. The CPU's job is to execute instructions, which are like tiny commands that tell it what to do. These instructions are written in a low-level language called assembly language. Assembly language is a human-readable representation of CPU machine code, where each assembly instruction corresponds to a specific CPU operation. For example, an instruction might look like this. This tells the CPU to move data from one register to another. There are many other instructions, like adding numbers, copying data from memory to registers, or storing data back into memory. A modern CPU can execute billions of instructions per second. For example, a 3 GHz processor can theoretically handle 3 billion cycles per second, with each cycle often executing one or more instructions. That's why your computer feels so fast. Now, if you create a set of these instructions to perform a specific task, it is called a program, which is stored on your disk. When you run a program, operating system loads it from the disk into the computer's RAM. This loaded program occupies a specific portion of memory, and it's organized into 4 key sections: stack, heap, text, and data. Let's break down each section of a program's memory, one by one. Stack. Think of this as a scratchpad for quick, temporary work. It stores things like function parameters, local variables, and return addresses. Heap. This is the program's flexible storage area. Whenever you create something at runtime, like a list or an object that can grow or shrink, the memory comes from the heap. Text. This section contains the actual code instructions that the CPU executes. Data. Finally, the data section is where global and static variables live. These are values that stick around for the entire runtime of the program, such as constants or configuration settings. At this stage, the program is loaded into memory, but it's not yet a process. Also, for every program, separate block of memory is allocated. So, what turns a program into a process? A process is a program in execution. When the operating system decides to run a program, it assigns it a process control block, PCB, which we'll talk about later, and starts executing its instructions. The CPU has a special register called the program counter. This register holds the memory address of the next instruction to execute. At the start of a program, the program counter points to the first instruction in the text section. After each instruction is executed, the program counter updates to point to the next instruction. If the program has loops or conditions, the program counter might jump to a different memory address to execute a different part of the code. Here's a small but important detail. The CPU doesn't care about the program's purpose, it just follows the instructions in order, guided by the program counter. Now, if only one program were running at a time, process management would be straightforward. But in reality, your computer is juggling dozens of programs, like your web browser, music player, video games, and more, all running seemingly at once. This is where things get interesting and complex. To understand how the operating system manages all these processes, let's look at the process model. In this model, every runnable program on the computer is treated as a process, and each process has its own virtual CPU. This is an illusion. The computer doesn't have a separate CPU for each process. Instead, the real CPU switches between processes, giving each one a turn to run. This switching is called context switching. During a context switch, the operating system saves the state of the current process, like the program counter and register values, and loads the state of the next process. This ensures that each process picks up exactly where it left off. Context switching is super fast, but it does take some time, so the operating system tries to minimize it to keep things efficient. For storing the context of processes, Process Control Block or PCB is used. The PCB is a simple data structure. Think of it as a record or object in memory that the OS maintains for every single process. It's uniquely identified by an integer called the process ID, or PID. You can see these in tools like Task Manager on Windows or Top or PS on Linux Mac. The PID helps the OS quickly reference and manage processes. The PCB stores all the vital info needed to track and resume a process at any time. Without it, switching between processes would be impossible. Here's a breakdown of the key pieces of information it holds. Process state. This stores the current state like new, ready, running, etc. of a process. This tells the OS at a glance where the process is in its life cycle. We will talk more about this later on. Program counter. This gives the address of the next instruction to execute. When the process resumes after a switch, this picks right up where it left off. CPU registers. This stores snapshots of all the CPU's registers, like accumulators, index registers, and status flags, at the moment of suspension. Saving and restoring these is part of what's called a context switch, the brief handover when the OS pauses one process and starts another. Priority and scheduling information. This stores the number or value showing how important this process is. Higher priority might mean it gets the CPU more often, useful for real-time tasks like video streaming. It also includes pointers to scheduling queues. Memory management information. It stores details on the process's memory layout, like base and limit registers, to bound its access, page tables, for virtual memory, where the OS tricks the process into thinking it has more RAM than physically available by swapping to disk or segment tables. This prevents one process from accidentally, or maliciously, accessing another's memory. I/O status information. It stores the lists of open files, devices in use, like printers or network ports, and allocated I/O resources. It tracks file descriptors and ensures only the owner can access them during waits. Accounting information. This stores usage states, like how much CPU time it has consumed, elapsed wall clock time, number of I/O operations, and limits, example, max memory allowed. This helps the OS bill users and multi-user systems, detect resource hogs, or enforce quotas. When a context switch occurs, the OS saves the current process's PCB to memory and loads the next ones. This whole mechanism allows for smooth multitasking. In modern OCs, processes can even spawn child processes. For example, when a web server forks a new instance to handle an incoming request. When a process is active, it doesn't just stay in one mode forever, it transitions through several distinct states, managed entirely by the OS. It is called the life cycle of a process. These states help the system keep everything organized and responsive. In most operating systems, there are 5 primary states a process can be in at any time. New, or start. This is the very beginning. When you launch a program, the OS creates a new process entry. The process is being set up, resources are being allocated, like memory space, and initial bookkeeping is done. But it's not ready to run yet. The OS might limit how many processes can start at once to avoid overwhelming the system. From here, it moves to ready once setup is complete. If creation fails, say, out of memory, it might get terminated right away. Ready state. Now the process is all prepped and waiting in line for the CPU. It's loaded in memory, has its resources, and is eager to go, but the OS scheduler hasn't picked it yet. There might be a queue of ready processes, prioritized by things like urgency or fairness. For example, your video editor might jump the line over a background update. Processes arrive here after the new state, or they can return here if they were running but got interrupted. The goal is to minimize time spent waiting here to keep the system snappy. Running. This is the action state. The OS scheduler assigns the CPU to this process, sets its state to running, and lets it execute instructions. The program counter advances, registers update, and work gets done. But running doesn't last forever. A process might only get a time slice, like 10 to 100 milliseconds, before the OS switches away to give others a turn. This prevents any one process from hogging the CPU. Waiting, or blocked, state. Sometimes, a running process has to pause because it's waiting for something external, like user input from the keyboard, data from a network connection, or a file to finish writing to disk. It can't proceed without that resource, so the OS moves it to waiting, frees up the CPU for someone else, and puts it in a waiting queue. Once the event happens, for example, the key is pressed, an interrupt signals the OS to move it back to ready. This state is crucial for efficiency. Without it, the CPU would idle uselessly. Terminated, or exit, the end of the line. When a process finishes its task, like closing an app normally, or gets forcefully stopped, due to an error, user kill, or OS decision, it enters terminated. Here, it stops executing, and the OS cleans up, deallocates memory, releases files and devices, and removes the process from the system. It lingers briefly in this state to allow any parent processes to check its exit status, success or failure code, then it's fully removed from memory. Poor cleanup here can lead to zombie processes, ghosts that waste space until reaped. These transitions aren't random, they're triggered by events like system calls, requests from the process to the OS, hardware interrupts, from devices like timers or keyboards, or software interrupts. For instance, a timer interrupt every few milliseconds forces a check to see if the current process's time slice is up, leading to a switch. This whole system ensures fairness and responsiveness. Your mouse doesn't freeze while a heavy calculation runs in the background.